Welcome back. We'll start this section by explaining what white noise is and why we need to understand it when picking the correct model for a time series. Let's start with the definition. White noise is a special type of time series where the data doesn't follow a pattern. You can probably recall one of the assumptions of TS data, that patterns found in the past also persist in the future. In this case, since no pattern can be found, we can't predict white noise. Additionally, in order to consider a series as white noise, it needs to satisfy the following three conditions by having a constant mean, a constant variance, and no autocorrelation in any period. The first two requirements are rather straightforward, but we can certainly try to iterate a bit more on the last one. In case you need a hint, autocorrelation measures how correlated a series is with past versions of itself. But we will elaborate more on this definition later in the section. For now, all you need to know is that no autocorrelation means there is no clear relationship between past and present values of a time series. Thus, white noise is a sequence of random data, where every value has a time period associated with it. We can say it behaves sporadically, so there is no way to successfully project it into the future. Okay. In financial modeling, it is important to distinguish white noise data from regular time series data. We can easily tell the two apart by comparing their graphs. To demonstrate, we can generate white noise data and plot its values. Then, we can try plotting the graph of the S&P closing prices and compare the two. Let's start by generating the white noise series and storing the values in a variable called WN. To achieve this, we can use the help of the random normal method, which is part of the numpy package. This will create an array of random values from a normal distribution. Well, if we want this sequence to be comparable to the S&P one, we should set its mean and standard deviation to that of the actual set. For convenience, Pandas provides methods called mean and STD, which estimate those values for an attribute of a data frame. So far, so good. Now, the location argument of the method called LOC takes numbers for the average point of the distribution. Therefore, we set LOC equal to DF market value mean. Similarly, the scale parameter indicates how wide the distribution is. So, we set it equal to DF market value STD. Right. Before calling the method, we define how many values we want to generate. If we want the sequence to serve as a good comparison, it should have as many elements as our time series. So let's set the size argument equal to LEN DF, and then run the cell. Subsequently, try adding the white noise to the data frame. The line of code to achieve this is the following. DF bracket WN bracket equals WN. This will add a new column to the data frame titled WN, which is short for white noise. Then, every value of this sequence will be assigned to a time period, since the data frame uses dates as indices. Good. Now let's see what the data frame looks like after adding the new column. As you can see, the mean of the two columns is similar, but not entirely equal. The reason is that the white noise values we generated are normally distributed around the mean of the S&P. However, since each one is generated individually, the average does not have to end up being the same. Anyhow, to get a better sense of what white noise data looks like, we should graph it using the plot method. The plot method on the WN attribute of the data frame can help us plot the newly generated data. It is generally a good practice to name your graphs to avoid confusion when extracting insights. So let's title the plot with something appropriate like White Noise Time Series. Moreover, to make these titles more easily distinguishable, we can make them larger. One way to do this is by passing a numeric value, like 24, to the size argument of the title method. If we run the cell, we can see there is no clear pattern in the data, apart from most values forming around the mean. Since we have many observations in the set, we can try stretching the figure to get a better idea of the graph. In order to do so, let's set the fig size argument equal to 20, 5. Now, if we take a look at the elongated figure, we will clearly see how many of the values are within some proximity of the mean of S&P prices. Great job! Next, we need to plot the S&P prices for comparison. To achieve this, we only need to run the plot method on DF market value. Once again, let's try setting the appropriate title and figure size for a better comparison. It's easy to see the vast difference between the shapes of the two graphs. It will be even easier to compare them if they have the same magnitude. Let's do that by setting the plot of S&P prices to go from 0 to 2300, just like the white noise prices do. The relevant code is plt.y_lim from 0 to 2300. This sets the limits of the y-axis of our graph. Okay, you may have noticed there are far smaller jumps between periods for S&P values. Since the prices are non-random, we need to recognize the pattern to make accurate forecasts. Great job! Next time, we'll discuss another peculiar type of time series called a random walk. Thanks for watching. Hello there. Now that we've learned what white noise data looks like, let's shift our focus to a different type of time series called a random walk. For starters, let's begin with the definition. A random walk is a special type of time series where values tend to persist over time, and the differences between periods are simply white noise. Now, suppose we express prices with capital P and residuals with epsilon. Then an example of a random walk would be any process for which prices in period t equal prices in period t-1 plus some residual. Of course, we assume the residuals are white noise, so they are arbitrary and cannot be predicted. This suggests that the best estimators for prices today are prices yesterday. As we mentioned in the previous lecture, in time series data, patterns observed in past data will persist in the future, so the best estimators for tomorrow's prices are today's prices. Nevertheless, we can't possibly predict how prices will move in the future with great accuracy. Moving on. To get a better idea of what a random walk process looks like, we're going to load some data and plot it against the S&P prices for comparison. For your reference, the data is stored in the rand walk file accompanying this lecture. In case you haven't downloaded it yet, now would be a great time to do so and store it in the same directory as your Python notebook files for this course. Well, we already saw how to convert the dataset in the previous section. Let's recap by quickly going over all the steps once again. We can start by loading the data using the read CSV method and saving it into a data frame called RW. Of course, RW is just short for random walk. Then we need to change the date column into a date time type. Once we're ready, we must set these dates as indices and define the frequency as business days. I'm sure the code looks familiar, so we won't go over it in detail. Next, it's time to observe the summarized statistics for the new time series using the describe method. It's important to note that the column of interest is called price because we want to add its values to our existing data frame. That's why we write df rw equals rw price. Last but not least, make sure to check the top observations of the data frame to see if we have successfully added a column to our data frame. Great job! Now let's plot the random walk data and see what it looks like. As a logical step, we can call the plot method for the RW column and set appropriate values for the fig size and title arguments. After we run the cell, we will see a graph which significantly differs from the white noise one. In fact, the random walk data is much more similar to S&P prices than to white noise values. We can try plotting the two-time series on the same graph to make a better comparison. So let's call the plot method on both the RW and market value columns of the data frame. Once again, we should remember to set an appropriate name to the graph before running the cell. Whoa! Surprisingly enough, the two-time series look somewhat similar. Both have small variations between consecutive time periods. What's more, both have cyclical increases and decreases in short periods of time. Great job!
In finance,
There's a popular term called market efficiency. Broadly speaking, it measures the level of difficulty in forecasting correct future values. In general, if a time series resembles a random walk, the prices can't be predicted with great accuracy. Conversely, if future prices can be predicted with great accuracy, then there are arbitrage opportunities. We can speak of arbitrage when investors manage to buy and sell commodities and make a safe profit while the price adjusts. Now, according to theory, if such opportunities exist within a market, investors are bound to take advantage, which would eventually lead to a price that matches the expected one. As a result, prices adjust accordingly. That's why we usually expect most markets to be more or less efficient. Okay, that's enough theory for now. The two concepts we just explored, white noise and random walk, sound quite similar, but from their plots we realize that in fact they aren't. Great. Next time we will introduce the notion of stationarity and explain the difference between the two. Thanks for watching. Welcome back. As you probably recall, our last lecture touched on the notion of stationarity. Technically speaking, time series stationarity implies that taking consecutive samples of data with the same size should have identical covariances, regardless of the starting point. This characteristic of the data is also known as weak form stationarity, or covariance stationarity. Let's elaborate a bit further. We can classify a time series as covariance stationarity if it satisfies three key assumptions. First, having a constant mean, and second, having variance. The third one requires the data to have consistent covariance between periods at an identical distance from one another. In other words, we want to have the same covariance between the first and fourth period as we do for the third and sixth, since they are 3 intervals apart. An obvious example of a weak form stationary process is white noise. As we've discussed before, the mean for white noise is always 0, and the variance stays the same. Additionally, autocorrelation between lags is always 0. Since covariance is simply correlation multiplied by the standard deviations, it would also equal 0. Therefore, white noise really satisfies all the assumptions of a covariance stationary process. Before we move on, we have to be perfectly honest with you. When it comes to a proper definition of stationarity, we must note it actually refers to strict stationarity, where samples of identical size would have identical distributions. In math terms, this means that for any strictly stationary random variable x, the distributions between x, t, and x, t plus k should be the same as the one between x, t plus tau and x, t plus k plus tau for any natural number tau. Since this case is very restrictive, we rarely observe it in the natural world. Hence, in analytics, it is universally accepted to use stationarity to describe covariance stationarity. So we will stick to this definition. Okay. Now that you know what stationarity is, you're ready to learn what tools we use to determine its existence in our data. Fantastic. Thanks for watching. Hello there. To conduct proper time series analysis, it is vital to determine whether the data follows a stationary or non-stationary process. Lucky for us, in the 20th century, statisticians David Dickey and Wayne Fuller developed a test to help all of us time series analysts check whether a dataset comes from a stationary process. We call it the Dickey-Fuller test, or DF test for short. Later, an augmented version of the test was developed to account for time dependency in the data. In this lesson, we will learn how to use it. Let's begin. First, we should get familiar with the null and alternative hypothesis. The null of the Dickey-Fuller test assumes non-stationarity. More precisely, it assumes that the one-lag autocorrelation coefficient is lower than 1. When we've computed the test statistic, we can compare it to the critical value in the Dickey-Fuller table. If the test statistic is lower than the critical value, then we reject the null, so the data comes from a stationary process. Great job! Now let's see how we can implement this into Python. For starters, we need to use the AD-Fuller method from the Stats Models TSA Stats Tools package. We've already imported the library as STS, so we write sts.adfuller. In the parenthesis, we need to select what time series we are analyzing. Therefore, we should write df market value and run the cell. Let's go over the outputs of the Dickey-Fuller test and understand what the values represent. On the first line, we see the test statistic from running the test. As we mentioned, we can compare it to certain critical values to determine whether we have significant proof of stationarity. Conveniently enough, Python also provides us with the 1, 5, and 10% critical values from the Dickey-Fuller table. Having all three comes in handy because we might use any of them as levels of significance in our analysis. Furthermore, you can notice that the t-statistic is greater than each of the critical values. Thus, for all of these levels of significance, we do not find sufficient evidence of stationarity in the dataset. The second line of the results expresses the p-value associated with the t-statistic. Let's take a second to observe how the p-value equals 0.41. This suggests there is roughly a 40% chance of not rejecting the null, so we can't confirm the data is stationary. The third line represents the number of lags used in the regression when determining the t-statistic. In this case, we have 18, so there is some autocorrelation going back 18 periods. Of course, we'll take this into account when picking the appropriate model. Moving on to the next line, it expresses the number of observations used in the analysis. This value depends on the number of lags used in the regression, so the two should usually add up to the size of the dataset. Now, the last line of the code estimates the maximized information criteria provided there is some apparent autocorrelation. The lower the values, the easier it is to make predictions for the future. To provide some comparison to what these results mean, let's run the test for the white noise data we generated earlier. We know that white noise is a stationary process, so we expect to get a very low p-value. Additionally, since there is no autocorrelation in white noise, there should be no lags involved in the regression. Try running the code. There, we see exactly what we expected: a p-value close to 0 and no lags being part of the regression. Okay, let's also run the augmented Dickey-Fuller test for the random walk data. We only need to change the argument we provided to the method from dfwn to dfrw. So when we print out the results of the test, we will see a p-value of around 0.62. We don't have significant evidence to identify this time series as stationary. In fact, based on the p-value, there is more than a 60% chance the data comes from a non-stationary process. More often than not, random walk intervals of the same size differ significantly due to uncertainty of the process. So each day's price might go up or down, but the starting position is always different. Moreover, chance dictates that we can have intervals of alternating ups and downs in prices, as well as once with constant increase. The covariances of two such intervals with identical size would very rarely be equal. Thus, unlike white noise, we expect them to be a non-stationary process. Hence, these results satisfy our expectations. Fantastic! We observed how different the Dickey-Fuller results for a stationary and non-stationary process are. Testing for stationarity will feature in the analysis of any dataset we come across for the remainder of the course. Therefore, the knowledge we just acquired will be of paramount importance in our time series analysis. In the next lecture, we will explore yet another peculiarity we sometimes observe in time series data: seasonality. Thanks for watching.
Hello again. Toward the end of the last section, we introduced a new term called seasonality. Now we have the chance to clearly explain what it means. Well, seasonality suggests that certain trends will appear on a cyclical basis. For instance, temperatures rise and fall based on the times of day and months of the year. These are two distinct seasonal pattern examples we observe in our daily lives. There are several ways of testing for seasonality. One approach is to decompose the sequence, where we split up the time series into three effects: trend, seasonal, and residual. Of course, the trend represents the pattern consistent throughout the data. Seasonal expresses all cyclical effects due to seasonality. Finally, the residuals are the error of prediction or the difference between the actual data and the model we fit. All right, the simplest type of decomposition is called naive. With naive decomposition, we expect a linear relationship between the three parts and the observed time series. Now, let's pay attention to the two main approaches to naive decomposition: additive or multiplicative. Additive assumes that for any time period, the observed value is the sum of the trend, seasonal, and residual for that period. Similarly, the multiplicative decomposition assumes the original series is a product of the trend, seasonal, and residual values. To make things more convenient, the stats models package includes a method called seasonal decompose that takes a time series and splits it up into the three parts. Well, now it's time to observe how this method works in practice. First, we need to store the output of the method in a variable. Since we are measuring seasonal decomposition, we shall call it sdec. Next, we should call the method seasonal decompose and provide dfMarketValue as an attribute. In addition, we need to define whether we want to compute additive or multiplicative decomposition. Let's start with the additive approach. We can add additive to the name of our variable to avoid confusion. Try setting the model attribute equal to additive. To analyze the outcome, we should graph the results, so we'll use the plot method next. Depending on your version of Python, you may also need to use the pltShow method to display the graphs. Okay, let's have a closer look at the results. As you can see, the trend closely resembles the observed series. That's because the decomposition function uses the previous period values as a trend setter. We've already determined that current period prices are the best predictor for the next period's prices. If we observe seasonal patterns, we'll have other prices as better predictors. For instance, if prices are consistently higher at the beginning of the month compared to the end, we'll be better off using values from some 30 periods ago than from one period ago. The trend part of the decomposition explains most of the variability of the data. The seasonal plot looks like a rectangle. This happens when the values are constantly oscillating back and forth, and the figure size is too small. In our case, the linear change results from constantly switching up and down between -0.2 and +0.1 for every period. Therefore, there is no concrete cyclical pattern determined by using naive decomposition. The residuals are the errors of our model estimates. Essentially, they are the difference between true values and predictions for any period. As you can see, the residuals vary greatly around the turn of the century and around 2008. This can be explained by the instability caused by the .com and housing prices bubbles, respectively. Overall, the results of the additive decomposition suggest no seasonality in the data. Let's double-check this result by computing the multiplicative decomposition as well. To do so, we simply need to change the value we assign to the model argument from additive to multiplicative. If we run the cell, we see very similar results to the first decomposition. The seasonal sequence has no clear pattern once again, and the trend closely resembles the observed series. Thus, we have further proof there is no seasonality among S&P prices. Great! Since the trend follows actual data closely, next time we will have a closer look at the correlation between past and present values. Thanks for watching. Hello again. Based on what we've learned so far, we know that we avoid shuffling time series data because we want to preserve the chronological order of the set. Well, one of the main reasons is that we often discover links between past and present values within T-series data. Mainly, we find some relationship between the entries for consecutive periods, T, and T-1. All right, before we dive into the specifics, let's define some important terms. For starters, correlation measures the similarity in the change of values of two series. In this case, though, we only have a single variable. To calculate the similarity in a single time series change through time, we need to introduce a new concept: autocorrelation. As the name suggests, autocorrelation represents the correlation between a sequence and itself. More precisely, it measures the level of resemblance between a sequence from several periods ago and the actual data. Such a series is called lagged because it is essentially a delayed version of the original one. For instance, if we find the autocorrelation for a time series with daily frequency, we are determining how much of yesterday's values resemble today's values. If the frequency is instead annual, autocorrelation will measure the similarities from year to year. Fantastic! Since autocorrelation is such a vital part of data analysis, in the next video, we will explore how to compute it. Thanks for watching. Welcome back. In time series analysis, it is vital to compute and compare autocorrelation values between different lags. To do so, we need to introduce the autocorrelation function, or ACF for short. The ACF computes the autocorrelation value for however many lags we are interested in simultaneously. The alternative would be manually finding the correlation between our original data and multiple lagged versions of itself. Quite convenient. The Stats Models Graphics TSA Plots package contains a method for plotting the autocorrelation function. We'll take advantage of it and use it to analyze time dependencies more efficiently. Okay, let's get coding. We'll start by calling the plotACF method from the TSA Plots package. Since we imported the library as SGT for convenience, we'll write sgt.plotACF. In addition, before running the cell, we need to pass values to some of the arguments of the method. For starters, we must set time series we want to analyze. In this case, we want to find the ACF for the market index we are interested in. So we type DF market value in the parenthesis. Next, we have to assign a number to the lags argument because the default is the length of the time series. In a set with thousands of observations, computing so many lag values would be extremely time-consuming and unnecessary. In time series analysis, common practice dictates analyzing the first 40 lags, so we set the lags equal to 40. Keep in mind that by saying the first 40 lags, we mean the last 40 periods before the current one. Right. We can also set the 0 argument equal to false. This argument indicates whether we include current period values in the graph. For correlation functions, this is unnecessary, because the correlation between a value and itself will always be 1. This will lead to always having the first bar of the graph equal to 1, which makes the plot more difficult to comprehend correctly. Therefore, setting the argument equal to false ensures we only observe a plot for higher lag values. As a final step, we should name the graph to avoid confusing similar graphs throughout our analysis. Adding titles to plots is a good practice in general because it makes it easier to keep track of the work you have done. You can also increase the size of the title to make it easier to spot. To do both of these, you simply need to call the title method and set the name and size as arguments. Use the PLT show method at the end of the cell. Let's examine the graph up close. Values on the x-axis represent lags. You can notice how they go up to 40, since that is what we set the lags argument equal to. Numbers on the left indicate the possible values for the autocorrelation coefficient. Correlation can only take values between -1 and 1, which is why the graph stops at 1. You probably figured this out, but the thin line across the plot represents the autocorrelation between the time series and a lagged copy of itself. The first line indicates autocorrelation, one time period ago. The second line represents the coefficient value for 2 periods ago, and so on. The blue area around the x-axis represents significance. The values situated outside are significantly different from 0, which suggests the existence of autocorrelation for that specific lag. Take a second to observe how this area expands as lag values increase. The greater the distance in time, the more unlikely it is that this autocorrelation persists. For instance, today's prices are usually closer to yesterday's prices than the prices a month ago. Therefore, we need to make sure the autocorrelation coefficient in higher lags is sufficiently greater to be significantly different from 0. Great. Notice how all the lines are higher than the blue region. This suggests the coefficients are significant, which is an indicator of time dependence in the data. Moreover, we can see that autocorrelation barely diminishes as the lags increase. This in turn suggests that prices, even a month back, can still serve as decent estimators. Fantastic. Before we move on, let's examine the ACF of the white noise series we generated earlier. Being able to tell white noise apart from regular time series data is fundamental in modeling, but there'll be more on that toward the end of this section. In order to determine and plot the ACF of the white noise we generated, we should only change the sequence of values we are passing to the argument, from DF market value to DFWN. Let's pay attention to the plot and how it is completely different from the one for closing prices. For starters, we have values going either way, so there are patterns of positive and negative autocorrelation. This contrasts the ACF for closing prices, where all values were positive. Also, observe how all the lines fall within the blue area. Thus, the coefficients are not significant across the entire plot. This suggests there is no autocorrelation for any lag, which is one of the assumptions of white noise data. For homework, you can check the ACF for a random walk and try to analyze and interpret the results. Marvelous work, everyone! In the next lecture, we will explain why the ACF plot for S&P prices looks the way it does and introduce partial autocorrelation. Thanks for watching. Welcome back. Autocorrelation measures the similarity between a time series and a lagged version of itself. However, the coefficients also capture secondhand effects. For instance, examine the value of the autocorrelation coefficient for the third lag. It captures direct and indirect ways in which the lagged series affects the original one. By indirect, we refer to all other channels, through which past data affects current data. In this specific case, these secondhand effects come in the form of prices 3 days ago, affecting value 2 and 1 day ago, which in turn affect present prices. If we wish to determine only the direct relationship between the time series and its lagged version, we need to compute the partial autocorrelation. To do this, we can use a function like the ACF, called the partial autocorrelation function, or simply PACF. Let's get coding and plot the PACF for S&P 500 closing prices. Conveniently enough, the Stats Models TSA Graphs package we imported earlier also includes a function called plot PACF. Much like its ACF counterpart, the plot PACF method requires defining several arguments. And just as before, the first one is the time series we are examining. The second one is the lags argument, which we will set to 40 once again. As stated before, 40 is the optimal number of lags we usually choose for time series analysis. Next, just like with the ACF, we set the zero parameter to false. Since there are several ways of computing the PACF, we need to define what method we want to use. In this instance, we will rely on the order of least squares, or OLS for short. Hence, we set the method argument equal to OLS. Before calling the method, it's important to title the plot to avoid confusion later. You can also increase the size of the title to make it easier to spot. Use the PLT show method at the end of the cell. Let's run the code. Now we should take some time to observe the plot in more detail. Only the first several elements are significantly different from zero, a tremendous contrast to the ACF plot, where all values up to 40 lags were significant. Also, some of the values, like the 9th lag, are negative. This means that higher values 9 periods ago result in lower values today and vice versa. The difference between the two graphs comes from the way the PACF works. It cancels out all additional channels in which a previous period value affects the present one. For instance, the PACF measures the effect values in period t-2 have on values in period t directly. Compared to the values from the ACF function, the PACF ones cancel out the effects prices 2 days ago have on prices yesterday, which in turn affect prices today. Therefore, the ACF shows the combined effect of the prices from 2 days ago, both direct and through yesterday's prices, while the PACF only shows the direct effect. However, we must note that ACF and PACF values for the first lag should be identical. This is because there are no other channels through which past values can affect present values. Also notice how most values after the third lag are within the blue area. This means they aren't significantly different from zero, so the numeric values attached to them are not important. Since we can assume they are all essentially zero, being positive or negative is somewhat random without any lasting effects. Right. We have random walk and white noise data, so let's check out what their PACF plots look like. Let's start with white noise. By definition, there should be no autocorrelation between the elements of a white noise sequence. Thus, we expect the values for all periods to be insignificant. To plot the graph, we can copy the code from earlier and only change the time series from DF market value to DFWN. As anticipated, most of the values aren't significantly different from zero. Some of the coefficients can end up outside the blue area and seem significant, but that is completely random. This aligns with our previous assumption that there exists no autocorrelation in white noise. As a practical exercise, you can plot the PACF for the random walk data and then analyze and interpret its coefficients. Fantastic! Now that we've introduced the ACF and PACF, we can discuss what makes a model a good fit. Thanks for watching.